So this video starts the discussion of Chapter 18, carboxylic acid derivatives. By the end of this lecture, you should be able to say, I can recognize structure and use nomenclature for various carboxylic acid derivatives, explain and predict trends in reactivity among a set of related carboxylic acid derivatives by applying my knowledge of resonance and inductive effects, draw mechanisms for acid-catalyzed acyl substitution reactions, draw mechanisms for base-catalyzed acyl substitution reactions, and explain and predict trends in reaction mechanism among a set of nucleophiles by applying my knowledge of relative nucleophilicity and basicity. We're going to start with a brief overview of some structures and nomenclatures of carboxylic acid derivatives. On this slide, we'll talk about carboxylic acid halides and anhydrides. We can think about acid halides as a more reactive version of carboxylic acid, where we've basically switched the OH to a chloride to make a better leaving group. So here I'm just showing a generalized structure for an acid chloride. Take note that this part is called an acyl group, and when we use nomenclature to describe this kind of group, we say that it's an O-wheel group. So let's take an example to explain that. So if we take a look at this structure here, we have two carbons, so the root word is ethane. But on one of the carbons we have this acid chloride derivative, so we're going to say that this is ethane O-wheel chloride. Here's another example. We have a phenyl ring and then another carbon. So when we have phenyl and then CH2 and a functional group, then we call that part benzyl. And so here we're going to have benz O-wheel chloride. Some compounds also have a common name, so you probably recognize this example as acetyl chloride that we discussed in the last chapter, because when we have a CH3 and then a carbonyl, that functionality is usually referred to with the prefix acid. An acid anhydride is a functional group that's made by combining two carboxylic acids and doing a dehydration reaction, which is why it's called anhydride. So if we make the anhydride derived from acetic acid, then we get a compound called acetic anhydride. So all we do for the name is replace the word acid with the word anhydride. Similarly, if we take benzoic acid and we make that anhydride, we get benzoic anhydride. If the two carboxylic acids are next to each other on a ring, then when you make the anhydride, you get a cyclic anhydride. And these are usually referred to by their common names, and they're related to the acid they're derived from. So this is succinic anhydride. It's derived from succinic acid, which is the linear diacid precursor. So next we'll take a look at esters. When you're talking about naming for esters, you basically take this portion of the molecule, and that's the parent name, and then you use 8 instead of ic acid, and the name of this group goes at the beginning. So this ester is called ethyl butanoate. Here's another example. We have propionic acid. These three carbons make the propion, and then there's the ic acid. And then if we make the methyl ester of that, we have methyl propionate. Next we'll take a look at lactones. Lactones are just cyclic esters. So in this example we have S-beta butyrolactone. The name is derived from, here you have 4 carbons, so that's the butyr. And then if we label, we have the carbonyl carbon, then the alpha carbon, and then the beta carbon, and then this one would be gamma. The oxygen is attached at the beta carbon, so that's the beta. And then lactone describes just the functional group itself. And the S is for the stereochemistry at this carbon. This lactone also has 4 carbons, 1, 2, 3, 4. But the oxygen is at the gamma position. So this is gamma butyrolactone. This is a 7-membered ring, which is known as epsilon caprolactone. That's a common name that's used for it. And it can also be named by the IUPAC 6-hexanol-lactone. So the next functional group we'll take a look at is the amide. You should be at least nominally familiar with amides. In terms of naming, kind of depends. Here we have acetamide. Another example is hexanamide. So I've highlighted the hex part. Hexane, and then amide. Here's N-methyl acetamide. So we use this italic N to describe what group is attached to the nitrogen. So N-methyl, acetamide. Lactams are cyclic amides. Here's a special one, a solvent that we often use in solid phase peptide synthesis called N-methyl pyrrolidinone. And then here's caprolactam, kind of like the caprolactone, epsilon caprolactam. A related group is called the imide, which is a situation where you have kind of an amide, but that has another carbonyl next to it. So this is called an imide. This one is derived from succinic acid, and so it's called succinimide. We can also look at how phthalic acid can become phthalimide. One last related functional group is the nitrile. A nitrile is a cyano group that's bonded to a carbon atom. The common names for nitriles come from the parent carboxylic acid. So acetic acid, if we were to convert the carbonyl carbon to a nitrile, we would get acetonitrile. Similarly, if we had benzoic acid, it would become benzonitrile. Imides, and sulfonamides can also be acidic, depending, of course, on what your base is. And the extent to which it is acidic is going to depend, firstly, on whether you have a traditional carboxamide or a sulfonamide or an imide. And so the real effect here comes from, again, a combination of resonance stabilization of the conjugate base and inductive withdrawing effects of the adjacent groups. This takes on a little bit more meaning if you compare to ammonia. So when we deprotonate ammonia, the pKa for that NH bond is about 35. And so the effect of this acetyl group on the acidity of an NH is pretty significant, 10 to the 20th times more acidic than for ammonia. So we can look at this from both the resonance and an inductive perspective. So for resonance, we would push our pi bond up, and then, of course, the lone pair here can be donated in. So when we donate these lone pairs in, we're really able to increase the acidity of the hydrogens here on these nitrogens. In addition to this resonance withdrawing effect of the carbonyl, which takes pi electron density, there's a strong dipole moment in this carbonyl that's going to be pulling electron density through the sigma bond from nitrogen here. So this is the inductive withdrawing effect of the carbonyl, taking sigma electron density from nitrogen, whereas the resonance effect takes pi electron density. So both of these effects are at play, and both contribute to the increase in acidity of these NH bonds relative to ammonia. You can draw out similar effects for the benzene sulfonamide, succinimide, and phthalimide. So we're going to take a minute and go a little bit deeper here with amides, which are really critical in biology in a lot of ways. So let's draw the resonance structures one arrow at a time. So we can push pi electrons up onto this oxygen. Remember to use your resonance arrow. In the next structure, we're going to donate electrons in from the nitrogen. And so what you can see from these three structures is that the carbonyl carbon here, this is a pi bonded carbon. This one is also a p orbital, an empty p orbital. And then here it's also in a pi bond. So in all these three pictures, we have a p orbital at this carbon. We have a geometry here of 120, and we have a planar system. Okay, so you'll note that amides are completely planar. They have a higher rotational barrier about the carbon-nitrogen bond than a carboxylic acid or ester derivative would have, because this resonance contributor is a much stronger component of the overall structure than the similar structure for an ester would be. Because the lone pair on the nitrogen is spending so much time shared with this carbon, this nitrogen lone pair is not basic, and instead it increases the basicity of the oxygen, and so amides are basic at the carbonyl oxygen, just like a carboxylic acid, but to a much more dramatic extent. Similarly, the electron donating effect of this resonance contribution makes this carbon less electrophilic than other carbonyls. I already mentioned the large rotational barrier. The nitrogen atom is also sp2 hybridized, so that is because of what a strong contributor this last structure is. That pair of electrons, in order to be shared in a pi bond with this carbonyl carbon, has to be in a p orbital, which means that the remaining three are sp2. Carbonyls of amides are really exceptional hydrogen bond acceptors, and the amide NH is a great hydrogen bond donor. Again, because the lone pair here is being shared so much with the adjacent carbon, that makes this nitrogen less electron rich than it otherwise would be. That contributes to the increased acidity here on these NHs, and that makes them more delta plus, making them a better hydrogen bond donor. You can see the hydrogen bond in this charge density profile here. And this kind of interaction is really what drives the structure of proteins and other amino acid composed structures. Carboxylic acid derivatives all undergo a really similar set of reactions. It can feel overwhelming when you start to study this reactivity, because you might view each reaction as an individual item that you need to learn. It's really important that instead you group them up into two general classes of reactivity: reactions that are conducted under acidic conditions and proceed through activation of the carbonyl, and reactions that are conducted under basic conditions and proceed through direct addition of the nucleophile to the carbonyl. Those are the two main mechanisms, and then you'll have some small perturbations of the mechanism caused by changes in the nucleophile itself, but it's really not a significant difference from mechanism to mechanism. So you just need to get the general pattern down and then look at each individual nucleophile's contribution to later intermediates in the mechanism, and take note of those kind of changes that are caused. So we're going to look at a very generalized structure. We have an R group on one side, we have the carbonyl, and we have some leaving group. So this could be chloride or an OR or NH2 and related structures. We're going to have a generalized nucleophile. In acidic conditions, we're using the acidic conditions because we have a weak nucleophile. So that's very similar to the aldehyde and ketone conditions that you already learned for acetal formation. So we're going to use some protic acid. This can typically be used in a catalytic manner, although sometimes it's convenient to speed up the reaction by adding a lot more. And so our nucleophile is going to be something that has a lone pair. It might be oxygen or nitrogen or sulfur. And so the first step, because we're going to have a lot more nucleophile around, typically than we have of carbonyl, often it's run in a solvent, for example, methanol. And also because this lone pair is going to tend to be more basic than the carbonyl lone pair, the first step is going to be to protonate the nucleophile. Our next step is going to be to activate the carbonyl by deprotonating that species we just made. And now our weak nucleophile can add to the carbonyl to give oxygen its electrons back. Next, we're going to adjust our proton state. So start by getting rid of the charge you have. We can just use a general base to deprotonate here and give our nucleophile its electrons back. Don't forget to draw your side product. And then this is going to clue you to remember that now we want our leaving group to leave. We don't know what it is, but generally in these mechanisms, with the exception of chloride, you're going to need to protonate this leaving group. Okay, now our leaving group would like to leave, but the oxygen isn't that big of a fan of this leaving group, and it really wants to help it out the door. So don't forget to bring that pair of electrons and use it to kick out the leaving group. See you, leaving group. And so now in our last step, we just deprotonate this carbonyl to get to the desired product, and we reform our acid catalyst. Okay, so in basic conditions, you'll either already have a strong nucleophile, or you can generate a strong nucleophile from your weak one by deprotonating. Now the strong nucleophile can add without activation of the carbonyl. Now we have our tetrahedral intermediate, and the leaving group wants to leave. We're going to again use the lone pair to help it. So the last thing we're going to do in this video is take a look at the reactivity of the carbonyl carbon in these various species. So essentially the question is, which of these is most reactive to other nucleophiles? And so all you need to do really is look at what's attached to the carbonyl, and we actually can go ahead and insert into this series the stuff that we already know, which are ketones and aldehydes. So I've put them here because methyl is an inductively donating group. So that's going to be stabilizing to this delta plus, but not as stabilizing as the resonance donation of the lone pair on this oxygen. and that in turn is not as stabilizing to the positive, delta positive here as the lone pair on the nitrogen. So as the donating ability increases, the electrophilicity will decrease. Heading in the other direction, we have the aldehyde, which you can really think of as our kind of 0 point for reactivity, because the C and the H are very similar in electronegativity. Now, if we have a carboxylic acid as our group, you can think of, if this were leaving, it would be the carboxylate. So this oxygen is not donating like this one. Instead, this lone pair is being pulled in this direction. So we actually have the effect of that oxygen as pulling electron density away from the carbonyl carbon. So that's going to make the carbonyl carbon more reactive. Similarly, chloride is pulling electron density out of the carbonyl carbon through an inductively withdrawing effect. And so the most reactive carbonyl is going to be the acid halide, followed by the acid anhydride. Those two are relatively close. Then aldehydes, then ketones. Those two are relatively close. And then esters, and then amides are the most difficult to react with other nucleophiles. You can also consider the relative leaving group ability as a way to remember this. So the better the leaving group, the more electrophilic that carbonyl carbon is going to be. So if you have a halide, that's going to be the best leaving group and the most reactive carbonyl precursor, followed by, if you have a carboxylic acid as the leaving group, the alkoxide, and then the worst is trying to kick out Nr2-, which is a really terrible leaving group, actually, and difficult to do.